Okay, now we're looking at inverse functions. And so an inverse function undoes what was applied to the input value of another function. So let's kind of break this down. Let's make it real simple. So the inverse of addition is subtraction. The inverse of multiplication would be division. And so an inverse function is going to work the same way. Whatever was done to the input value, we're basically going to go backwards and undo it. And so let's look at a pretty simple example right here on the left. So my original function's right here. F of x equals 2x take away 3. So, and they won't always be this obvious, but the inverse operation of subtracting 3 would be to add 3. And then the inverse operation of multiplying by 2 would be to divide by 2. And so that's going to be our inverse function right there. And that's the notation that we use for inverse. It looks like an exponent, but it's not. Okay, so don't think of it as an exponent. It's just a notation to represent the inverse function. And so I have a little blurb over here about that. So it does not mean this. Okay, it doesn't mean to flip it right here. So just be careful about that. That's just a notation. And so also a couple other details about this. And so um, this line right here, y equals x, the inverse and the original function will be a mirror image across that line right there. So you can see that the green and the red line right here is a reflection across that y equals x value. And then here's kind of an idea of a mapping of what's taking place. So the original function, you plug in x, right? And you plug it into the function and it shoots out a new value, and we call that y, right? Then if you were to plug that value into the inverse function, it'll take you directly back to where you started. And that would be true for every single possible ordered pair, okay? And so I have an example here with 5. Now, this doesn't prove that these are inverse functions, but it's just to kind of give you a simple idea of how this works. So I'm going to plug 5 into the original function. So let's see. 5 times 2 is 10. 10 take away 3 is 7. So see, that took me to 7. Then if I take 7 and plug it into the inverse function, let's see. So I'm going to take that, plug it in right here. So 7 plus 3 is 10. 10 divided by 2. Oh, took me right back to 5. Now, doing that doesn't actually prove that they're inverses of each other, but it's just kind of give you a little example. The way we're going to prove it is by the upper diagram here. We're actually going to plug in x and leave it as x and simplify it. And that what that does is that proves it for the complete set, not just one individual value. And that's what we're going to look at next. So let's see. This part down here, basically, if you want to read over this, this basically is just exactly what I just kind of went over. Oh, one thing I will mention um, is that on the inverse function, let's see, that the table of an inverse function will have the x and y values interchanged with the original function. So if you were to make a table of values for this green one right here, so we can just make a little simple table real quick. So let's see, if I plug in a 1, 2, take away 1 is, or take away 3 is -1. If I were to plug in a 2, 2 times 2 is 4, 4 take away 3 is 1. And so if I were to make a table over here for my inverse function, what's going to happen is the the values are going to get flip-flopped. So if you look right here, if I plug in -1, let's see, -1 plus 3 is 2. 2 divided by 2 is 1. So you'll see those two switch places. Same thing with this other one. I'm going to switch it. I'm going to put the 1 for my x value. Well, let's see. 1 plus 3 is 4. 4 divided by 2 is 2. So you can see that would be true for all the ordered pairs. So basically, the domain and the range flip places for the original function, and then for the inverse function, they're going to switch. And that's kind of important if when you kind of get into the weeds on some of this stuff. This will kind of be an introduction. We won't get too deep into that, but we will kind of mention some of those issues as we go through some examples. Okay, so now here we go. How can I verify whether two functions are inverses of each other? Well, since the inverse of a function takes you back to where you started, the following holds. And this goes back to that graph I was showing you up above. I'll go back up there in just a second. If the f of x and g of x functions are inverses of each other, then basically, so if I substitute g of x into f of x, it should return me back to x. So see, I'm starting with x. I'm plugging in x to g. Then I plug g into f, and then it should bring me back to x. And I'll give you a picture right here. So here are my x values, right? So I'm gonna plug x into the g function. And so what's gonna happen is that's basically gonna take me to some y values, or basically I'm gonna call them g of x values, right? And that's synonymous for y, right? And then I'm going to plug that into the f function. And so now I'm going to have f of g of x, right? I'm plugging that into my f function, and then it's going to take me back to where I started. And so I don't want to just do a value. I want to leave it as a variable because then it covers the whole set of values that exist inside here. And so let me kind of go back up to this picture up here. So see, this is basically what we're accomplishing right here, this top part. If I use a number, I can't be certain that it wasn't just, one ordered pair that has that relationship. So this will prove it that it's going to be true for all ordered pairs in the relationship. Okay, so coming back down here, let me go, oops, jumping around on me. I'm going to go ahead and erase this so I can have room to do these problems. And so another important thing, though, to mention here is that it doesn't happen that often, but you do kind of have to be careful because you really kind of need to check it both ways. You need to plug the f function into the g function also and make sure it reverts back to x. We probably won't run into any of those issues here, but it's something that technically we're really supposed to, you really need to check both of these. And so we'll go ahead and do that. Um, so that's what we're going to do. So it says find f of g of x and g of f of x and determine whether each pair of functions f and g are inverses of each other. So it has to hold for both. Okay, it has to hold for both of these. So looking at this first one, we're going to do f of g of x, okay? So what is g of x? Well, g of x is this expression right here, so that's what I'm going to substitute in there. So f of x minus 8 over 3. And so now that's what I'm going to substitute into the f function right there. Okay, so we're going to get 3 times x minus 8 divided by 3, and then we have a plus 8 on the back right there. And so as I do my algebra right here, the 3's will cancel. I'm left with x minus 8 plus 8. And then the minus 8 and plus 8 are going to cancel each other out. And I'm left with x. Okay, everything looks good, but we have to, like I said, we have to be careful. And we have to check it going the other way now. And so now we're going to do g of f of x. And so this time we're going to plug this in for our f of x. We're going to substitute that in. So we're going to have a 3x plus 8 right there. And now we have to substitute it into the g function right there. So let's see, that's going to leave us with, 3x plus 8. And I'll try to color code this a little bit. Then we have a minus 8 and then divided by 3. So what's in green is what I substituted in for that x right there. And then once again, as we follow the algebra, what we'll do here is in the numerator, I have a plus 8 and minus 8, so we can cancel that out. So that will leave me with 3x over 3. And then we can cancel out the 3's. And we're just left with an x. So we went ahead and proved it by checking both ways. And if you look at example A, you can kind of see that, yeah, it kind of makes sense. I have a plus 8 and a minus 8, and I have a times 3 and a divide by 3. So sometimes it can be obvious, but you have to be careful. We are definitely going to look at some examples that are not obvious. You can't tell by just looking. Okay, let's look at B. So we'll do the same thing. So we're going to do f of g of x. And so we're going to replace g of x with this right here. So we're going to get f of x plus 5 over 9. And then we're going to substitute that into my f function right there. So we have 5 times, and then we replace the x with x plus 5 divided by 9, and then take away 9. Now, typically, if these are going to simplify into x, it kind of works pretty easily. It kind of like the first one where the 3's cancel and the 8's cancel and so on. Um, so here you're going to kind of see that, well, what I can't cancel the 5 and the 9, but I could distribute the 5, right? So let's see, I get 5x plus 25 over 9 and then take away 9. I can't cancel out the 9's. It's not, one's divide, one's minus, so those aren't inverse operations. I could get an LCD and stuff, but I don't really see this going anywhere. So if they are going to be inverses, it's gonna pretty much kind of happen organically. It's going to kind of happen naturally. Everything's going to happen real nice. And I don't see that happening here. So these are not inverses. So no, these are not inverses. By the way, yes, those were inverses on the first one because they simplified to x in both cases. Here it doesn't, and so you don't even need to bother with trying the other one. You could if you wanted to, just to play it safe. But once you can't kind of square that, then you can kind of just stop there. Okay, so a couple, now we're going to kind of take a little bit of a deeper dive on this, and we're going to talk about, do all functions have inverse functions? Okay, do all functions have inverse functions? Okay, well, let's review functions for a minute here. So if we remember functions, they have to pass a thing called the vertical line test, right? So if I have a graph, um, something like this is good. That would be a function, right? It passes the vertical line test, right? Passes vertical line test. Let's see what else. What about a parabola? We've worked with parabola, so let's see a parabola. Yeah, that looks good. It would pass the vertical line test, right? Um, so if you remember, the definition of an inverse is that x and y are going to swap places, right? They're going to swap. Well, that could create some issues for some of these functions, that when you swap the x and y values, um, we could have some issues here. So I'm going to kind of get a little technical, and then I'll try to simplify this explanation down for everybody. Here we go. From our previous knowledge, we know that a function is a relationship in which each input x results in a unique output y. Okay, and so that's kind of what I was going over up here. So every input of x up here, I get a unique output for y. So let me give an example of one that's not a function. So if I had something like that, right? That would what happens is when x is 0, I don't get a unique return value. I get two different values. So that's not unique. I'm getting two different things right there. I'm not getting a singular value in return. So that one would not be a function, right? Okay. So now as seen before, and I was speaking about this earlier, um, the x's and the y's trade places. And here's kind of the notation for that. So you have x, y, and then now the y becomes your x, and your x becomes your y for an inverse function to create it. Therefore, for every y, there must only be one unique x for a function to have an inverse function. So the whole idea of the vertical line test, basically, there's going to have to be a horizontal line test also, because for every y value, there can only be one x value in return, right? So because when they get flipped, that could cause some issues, right? And we're going to look at an example like that in just a minute. All right, so when a function has this trait, it is known as being one-to-one. So the trait that we're speaking of is where each partner is faithful, is one-to-one. And so if you look over here on the right, this is a one-to-one function because each one is paired up with only a single term. If you look at the one in the middle, it's a function, but the value right here, 8 for y, has two partners. It's not one-to-one, and that's okay. It's still a function. If you were to graph this, this is a parabola. It looks like this, which is fine. It's a function, but it's not one-to-one, which would mean you wouldn't have an inverse function that you could create from it. Now, there will be ways to work around that, and we'll talk about that also in a moment. And then the first one you can see is not a function because the problem is the x value is got two different partners, and that violates our parameters for creating a function in the first place. So basically, the takeaway from this, the short of it is you need to be one-to-one in order to qualify to have an inverse. So if we go back up here, my first example I had right here, let me get rid of these lines. If you look at the first one, this one would be a one-to-one function. If you look at the second one, it's not one-to-one because right here, I'm getting the same y value twice. So when x is, oh, I don't know, like -4, I'm getting a 3 up here. And when x is, whatever, +4, I'm getting a 3 also. And so the problem is it's not one-to-one. So it is a function, but it's not a one-to-one function. And then my last one, that's not even a function right here. That's not a function at all. Okay, so what we're going to do here is we're going to use graphs to kind of get an idea of how this looks. I just kind of did, but we're going to look at some of these here. So we're going to use a thing called the horizontal line test. So I mentioned that a little bit earlier. It works the same way as the vertical line, except you're going to do horizontal lines, and if it doesn't cross at more than one spot, then you can determine that it's one-to-one. So what we're going to do here is all these are given to us as functions. You can tell they all pass the vertical line test if you look at all four graphs, but not all four pass the horizontal line test. The first one does. If you look right here, it does. So yes, it's one-to-one. So yes. The second one, not so much, because you can see right here, we hit in two spots. So it's a function, you know, yes, it is a function, but it's not one-to-one. So no. And then let's see, the third one, yeah, you can see it hits in a bunch of spots right there. So that would be no. And then the last one, that looks okay to me. I don't see any issues with that. So yes, that is one-to-one. Okay. So we probably won't get too crazy with dealing with this issue, but it's definitely worth mentioning. But what we can do sometimes, if you look at the graph of part B right here, what you can do in order to make it one-to-one to where we could actually find an inverse function is you could limit the domain. You could say, you know what, let's limit this domain to from 0 to infinity. And so what that would do is that would get rid of this right here. And then all of a sudden, oh yeah, it would be one-to-one. Okay. So we can do that. So sometimes when we're dealing with equations, what we might do is we might adjust the domain to where it would be one-to-one and we can work with it. All right, so that's a good start. And then what we're going to do on the next video is we're going to give you an equation and we're going to we're going to come up with the inverse function.